So this video is on pi and psi weights of an ARMA 1-1 model. So we know an ARMA 1-1 model is given by xt minus phi1 xt minus 1 equals at minus theta 1 at minus 1. We could rewrite it in terms of the backwards operator, and we would have xt minus phi1 b times xt equals a sub t minus theta 1 b a sub t. And we have x sub t in common, so if I pull that out, I'd have 1 minus phi1b equals a sub t times 1 minus theta 1b. So the characteristic polynomial for the AR part is 1 minus phi1b, and the characteristic polynomial for the MA part would be 1 minus theta 1b. So we want to rewrite it as in terms of pi and psi weights. So where does this come from? This goes back to expressing an AR series as an MA infinity series. So first off, recall the definition of a linear filter. So while we represent the series in terms of noise components, a sub t. So we are going to try and do that to our ARMA 1-1 model. So I'm going to start with psi weights. So going back to the model, we have xt times 1 minus phi1b equals at times 1 minus theta 1b. I could rewrite this as xt equals at 1 minus theta 1b divided by 1 minus phi1b. And we require the absolute value of phi1 to be less than 1, which would give us stationarity. So I can now rewrite this expression as 1 minus theta 1b times 1 over 1 minus phi1b. Now, this right here is the infinite sum of a geometric series. So I can rewrite the expression as x sub t equals a sub t times 1 minus theta 1b times 1 plus phi1b plus phi1b squared plus phi1b cubed, and so on. Therefore, I would have a sub t times 1 minus theta 1b, 1 plus phi1b, plus phi1 squared b squared, plus phi1 cubed b cubed, and so on. And now I'm going to FOIL, so I could rewrite this as x sub t equals a sub t times 1 plus phi 1b plus phi 1 squared b squared plus phi 1 cubed b cubed minus theta 1 b minus theta 1 phi 1 b squared minus theta 1 phi 1 squared b cubed minus theta 1 phi 1 cubed b raised 4 and so on. So that would imply a sub t times 1 plus, I'm going to combine like terms, so the b terms I'd have phi 1 minus theta 1 times b, the b squared terms phi 1 squared minus theta 1 phi 1 times b squared, phi 1 cubed b cubed it should be cubed minus theta 1 phi 1 squared b cubed and so on. So a sub t 1 plus phi 1 minus theta 1 b plus phi 1 times phi 1 minus theta 1 b squared plus phi 1 squared times phi 1 minus theta 1 b cubed and so on. Here I'm going to define psi 1 equals phi 1 minus theta 1, psi 2 equals phi 1 times phi 1 minus theta 1, and psi 3 equals phi 1 squared times phi 1 minus theta 1. And you may say, well, what about the other sides? Well, if you observe closely, psi 2 is phi 1 times phi 1 minus theta 1, which is simply phi 1 times psi 1. Psi 3 is phi 1 squared times phi 1 minus theta 1, which is phi 1 squared psi 1, and it is the same as saying phi 1 times phi 1 times psi 1, but phi 1 psi 1 is simply psi 2. So psi 3 would be phi 1 psi 2. Now, if I use induction, we would say that we would have a nice little recursion. So in general terms, we would have, we define psi naught to be equal to 1. It is a definition. And psi 1 would be phi 1 minus theta 1. And psi k would be equal to phi 1 raise k minus 1 times psi 1, or psi k would simply be equal to phi 1 psi k minus 1. And that could only hold true for k greater than or equal to 2. So those are the psi weights. So what did we just do? We simply rewrote xt as at times psi naught plus psi 1 b plus psi 2 b squared plus psi 3 b cubed and so on, which would simply give us psi naught at plus psi 1 at minus 1 plus psi 2 at minus 2 plus psi 3 at minus 3 and so forth. So we started with an ARMA 1-1 model. Now, if you look at the right hand side, that pretty much looks like an MA model. So I could define new parameters here. I could define negative theta 1 prime at minus 1, negative theta 2 prime at minus 2, negative theta 3 prime at minus 3, and so on. So what we have is an MA infinity model with theta 1 prime, theta 2 prime, theta 3 prime, and so on as the coefficients. So those are what we call the Psi weights of an ARMA 1-1 model. Now, we move on to the pi weights. Of an ARMA 1-1 model. So we have the original model, xt, which is 1 minus phi1b equals a sub t 1 minus theta 1b. I could rewrite this as x sub t 1 minus phi1b divided by 1 minus theta 1b equals a t. The condition here is that we require the absolute value of theta 1 to be less than 1, which guarantees something called invertibility. So we do the same trick that we did previously. So we can write this as 1 minus phi1 times b multiplied by 1 over 1 minus theta 1b. Again, that is the infinite sum of a geometric series. So I could rewrite that as 1 minus phi1b times 1 plus theta 1b plus theta 1b squared plus theta 1b cubed, and so on. Now I'm going to FOIL 1 plus theta 1b plus, I don't want to skip a step here, 1 plus theta 1b plus theta 1 squared b squared, theta 1 cubed b cubed, and so on. Now I would FOIL, I'll have 1 plus theta 1b plus theta 1 squared b squared, theta 1 cubed b cubed, minus phi1b minus phi1 theta 1 b squared minus phi1 theta 1 squared b cubed minus phi1 theta 1 cubed b raised 4, and so on. Now we'll have to combine like terms, so xt 1 plus theta 1 minus phi1 times b plus theta 1 squared minus phi1 theta 1 multiplied by b squared plus theta 1 cubed minus phi1 theta 1 squared b cubed, and so on, and that would equal to a sub t, which I can rewrite as 1 plus theta 1 minus phi 1 times b plus theta 1 times theta 1 minus phi 1 b squared plus theta 1 squared theta 1 minus phi 1 b cubed, and so on. Here I'm going to define pi 0 to be equal to 1 and pi 1 would be theta 1 minus phi 1. Pi 2 would equal theta 1 times theta 1 minus phi 1, which is simply theta 1 times phi 1. Pi 3 would equal theta 1 squared times theta 1 minus phi 1, which is theta 1 squared times phi 1, which is the same as theta 1 times pi 1, theta 1 times pi 2. So again, we have a nice little recursion. So in general, we have pi naught equals 1, pi 1 equals theta 1 minus phi 1, and pi k is equal to theta 1 raised k minus 1 times pi 1, or pi k would equal to theta 1 pi k minus 1 for k greater than or equal to 2. So what we simply did is we have xt multiplied by pi 0 plus pi 1b plus pi 2b squared plus pi 3b cubed, and so on, which would equal to a sub t. If I distribute the xt, pi 0 is 1, so I would simply have xt plus pi 1 b times xt, pi 2 b squared xt, pi 3 b cubed xt, and so on. So applying the backwards operator, good God, I will have xt plus pi 1 xt minus 1 plus pi 2 xt minus 2 plus pi 3 xt minus 3, and so on. That would equal to at. So in short, we would have j equals having technical difficulties here. Must be something wrong. Let's try a different area. Sum j equals 0 to infinity, pi j, xt minus j equals a sub t. And that would be the AR infinity representation of ARMA 1.1 model. And typically we don't have to go to infinite terms, it's not necessary. We will simply truncate it to an ARP, and the same applies on the other side. And so if we go back, we would have a similar representation, the MA infinity side, and I could write it as xt equals a sub t minus j times theta 1 prime or theta j prime. So if we have to write it in terms of an AR infinity representation, we could simply say pi 1 equals negative phi 1 prime and write it in our standard representation of an AR model. So that would be the infinite representation of ARMA 1.1. We do have to keep in mind that this would only work if we have the invertibility constraints and the stationarity constraints working in favor.